Hey, thanks, everyone.
Hello, everyone. We're going to get started in just a moment. I'd like to say welcome to tonight's webinar, A Tornado Research, a look back at the 1974 super outbreak. We're just going to take a moment to let everyone get on in here and get settled. During tonight's webinar, if you have questions, please feel free to put them in the Q&A at the bottom of your screen. We're going to try and get to them when we can. We have a lot of presentations and a lot of information to get through from some fantastic speakers. So we're going to try and time things as we can, but we will try to get to every question. So please feel free to put those in whenever you have them in the Q&A. And I'd love to introduce today's moderator this evening. So thank you, Melissa, for joining us. Melissa Griffin currently serves as the Assistant State Climatologist at the South Carolina State Climatology Office. Melissa received a degree in meteorology from Florida State University and has worked in the weather and climate enterprise for the past 2 decades. Melissa is also involved in various climate-related weather outreach and education initiatives, including the Community Collaborative Rain, Hail, and Snow Network, COCO-RAS, and is the chair of the AMS Weatherband Committee that makes all of these webinars possible. So thank you very much for joining us this evening.
Thank you so much, Eric, for that introduction. I am excited to see so many participants tonight. We have, just to let our panelists know, we have over 100 people that have joined us this evening for this special 90-minute webinar. Traditionally, our weather band webinars run about an hour, but this is just one of those events that we wanted to spend some good time focusing on, and we've got some experts in the room for this. So just a quick overview. On April the 3rd and 4th of 1974, one of the most intense and widespread tornado outbreaks devastated 13 states and the Canadian province of Ontario. There were at least 148 tornadoes confirmed, and this outbreak holds the record for the most F5 tornadoes produced in a single event. And just the enormity of this particular event. I know that we are one of many different talks that are going on this evening throughout the U.S., throughout the eastern part of the U.S., especially in the Midwest, that are focusing on this particular event. And we are fortunate enough to have, I've got to say, just an all-star panel of people here with us today to talk about this event. So first, going to start off by introducing Stephen Weiss. He is retired in July of 2018 after 46 years of service with NOAA and the National Weather Service, including 44 years as the severe weather meteorologist at the Storm Prediction Center in Norman, Oklahoma, and in Kansas City, Missouri. While he was there, his work focused on predicting severe thunderstorms, producing tornadoes with damaging wind and hail across the nation. Steve played a key role in the creation and operation of NOAA's Hazardous Weather Testbed, or HWT, for those who like acronyms, which improves severe weather forecasting. And he's authored over 150 scientific papers. We're also joined by Steve Corfidi, a research associate with the University of Oklahoma's Cooperative Institute for Severe and High Impact Research. And he develops presentations and training modules in severe convective weather for the National Weather Service Warning Decision Training Division. He's previously worked within the National Weather Service Storm Prediction Center in 2016, and he has served as a lead forecaster for 22 years. He's responsible for issuing tornadoes and severe thunderstorm watches and outlooks for the continental United States. We're also joined by Bob Henson, a meteorologist and journalist based in Colorado, and he is one of AMS Weatherband's maestros, one of 2 that are actually on our presentation webinar tonight. Bob was a longtime editor and writer for the University Cooperation of Atmospheric Research, known as UCAR. He followed by a stint with Weather Underground. He's now a freelancer and serves on the AMS Council, or did serve on the AMS Council from 2018 to 2021, and is author of AMS books, The Thinking Person's Guide to Climate Change and Weather on the Air, A History of Broadcast Meteorology. Last but not least is Dr. Ashton Robinson Cook from Arkansas, who was born in Arkansas with a passion for severe weather and passion for severe and extreme weather. And he is also one of AMS Weather Band's maestros. He learned firsthand the perils of severe weather at a very young age when his family lived in a mobile home that was struck by a damaging straight line winds, possibly a tornado, at the age of 3. And this encounter fueled a passion for weather that has continued throughout his career, along with his numerous accomplishments. Thank you all so much for being here tonight. I am looking forward to this webinar. And we're going to kick it off with Steve Weiss. And Steve is actually going to spend the next 15 minutes or so talking about the operations of the Storm Prediction Center. So Steve, if you're ready to go ahead and screen share, we'll let you get started.
All right, let me give this a try. And let's see, I think we are ready to go.
You are good to go, sir.
Thank you, Melissa. I'm very honored and privileged to be able to spend some time with good friends tonight, folks that I worked with for many, many years, and I'm very happy to be here. What I want to do is take a look back and a glimpse of what forecasting severe weather was like back in the 1974 timeframe. I arrived at CELS in Kansas City about 3 months after the April 3rd outbreak in July of 74. So I wasn't there on the day it happened. I wasn't in the room where it happened, so to speak. But what I saw when I arrived in the summer of 74 was clearly evident of the practices at CELS during that particular time. And I do want to share some of these memories for me and to give you an idea of what it was like 50 years ago. So, let's see. There we go. All right, so when I arrived back in the 70s, it was very evident. You could see the foundations of severe weather forecasting that started in the late 1940s in the Air Force and then in the early 1950s in the U.S. Weather Bureau. There were pioneering methods back then, focused, of course, on observational data and use of observational data in short-term forecasting. The image on the left shows 3 CELS forecasters in 1956. The one closest to us, Joe Galway, was one of the original forecasters, hired in 1952 in Washington, D.C., and came out to Kansas City in 1954 when the CELS unit moved there. On the right is a bigger picture showing the plotting chart that at the time was on the wall again in the mid-1950s. But these pioneering methods continued to inform forecast techniques when I arrived in 1974. It all began back in 1948 at Tinker Air Force Base. A major tornado, damaging tornado, struck the base on March 20th of 1948. The base commander, General Borum, said, "We can't have this happen again." And he assigned E.J. Fawbush and Robert Miller, weather officers on the base, to study what happened meteorologically and try and develop forecast techniques so that they could anticipate this type of event again. And lo and behold, 5 days later, you can see these composite charts of weather features on the left, not exactly the same, but enough similarities that Fawbush and Miller said, gosh, could we have another tornado today? And as it turned out, very low probability event. There was another tornado that struck Tinker Air Force Base, and they were well on their way to becoming leaders in severe weather forecasting. One of the books that I had when I first started is this Technical Report 200. Like me, it's showing its age a bit. And this compiled a lot of the analysis and forecast techniques that the Air Force had developed starting in the late 50s. Severe weather air masses conducive to thunderstorms and severe storms, synoptic patterns, composite charts, specifics on squall line development, going through a list of forecast parameters, etc. One of the things I want to focus on is synoptic patterns and composite charts. This is their type B tornado pattern. It's a little hard to tell because it's in black and white, but you can see the 850 jet coming from the south, the 500 millibird jet coming from the southwest, where there's intersecting jets in parts of eastern Kansas, moisture in the low levels, dry intrusions coming in from the southwest, and the area that is hatched in here would be a prime area for severe thunderstorms and tornadoes. Now, the Air Force started forecasting severe weather in the 48, 49, and 50 timeframe. By 1951, Fawbush and Miller were forecasting tornadoes for all Air Force bases across the U.S. There was pressure on the Weather Bureau to issue public tornado forecasts, and the Weather Bureau established what became the Cell Center in Washington, D.C. in 1952. They moved to Kansas City in 1954, in part to be located in an area that has more frequent tornado occurrence. And work continued to be done in coming up with forecast techniques under the guidance and the leadership of the head of the unit, Don House. This is forecasting guide number 1. The Weather Bureau issued a number of forecasting guides in the mid-50s, temperature, precipitation. But forecasting guide number 1 was produced by the Severe Storm Center on forecasting tornadoes and severe thunderstorms. And in a similar way, they looked at climatology, air mass types, proximity soundings, thermodynamics, kinematics, and went through a tornado forecast example. This was from February 1st, 1955, a series of 3-hourly surface charts over a mesoscale region. This is one of the first times that higher frequency chart analysis from surface data was performed, and this was a case that produced significant tornadoes across parts of northern Mississippi and northern Alabama. There was one other thing that I want to focus on, and this is a famous research paper number 39 by Fujita, Neustein, and Tepper on mesoanalysis. And they called it an important scale in the analysis of weather data. This was very key work that set the CELS unit into learning how to pay attention to small scales in their analysis. On the right is an example that Fujita had produced. It utilized data from what was called the pressure jump network in the early 1950s in parts of the Plain States. There was a theory that Morris Tepper had proposed that intersecting pressure jump lines might be a favored location for tornadoes. As it turned out, the theory was determined not to be valid, but the high resolution data associated with the pressure jump network barographs allowed a lot of detailed analysis, and Fujita showed how you could use that data to come up with analyses such as that on the right. I always found it interesting in the forward of that, where Fujita, Neustein, and Tepper wrote, the mesoscale is either overlooked or intentionally ignored in much of the analysis being done today. Again, this was mid-1950s. And he said, the meteorologist will have to despair of being able to predict local weather unless he has an accurate knowledge of the mesometeorological scale. And from this came Fujita's analysis of convective mesosystems, mesohighs, wake lows, features such as that directly tied to convective thunderstorms. So if we look at 1974, I'm going to go through a series of sentences that show what we had available and was produced back at that time. There was a convective outlook only for the day 1 period. It was issued twice a day, 9Z and at 15Z. 15Z was issued after the upper air soundings came in, and it was for the convective day, the 24-hour period from 12Z to 12Z. It was only did not have probabilities in it. It did not have as many risk categories. It was more simplistic. I'll show you an example in a bit. Tornado and severe thunderstorm watches were issued, and watch status reports when there was a watch in effect. The status reports were somewhat of a combination of today's mesoscale discussion product along with the clearing information of a watch status report at that particular time. These were the products that were issued. Observational data was the key to the short-term forecasting it sells. Surface data, upper air data, and sounding analyses were the primary sources of information available, and the forecasters spent most of their time working with these types of data sets because there was little in the way of numerical weather prediction. There was some, but not that much. Radar information consisted of hand-plotted hourly radar summary charts from coded radar reports. We did not see radar information directly, but had to decode the radar reports, and they were hand-plotted and a composite made once an hour. I'll show you some of this in a little bit. Satellite information was somewhat in its infancy stages. A Satellite Field Services Station, or SFSS, run by NESDIS, was co-located at cells starting in 1972. Hard copy black and white images with about 30 minutes, maybe a little more of latency, were brought out to the forecasters to examine. And then using these images, an old-fashioned 16-millimeter movie loop was created and displayed every 6 hours. The forecasters would go into a separate room, start the projector, and you would watch a movie loop once every 6 hours. That went back a good 6 to 12 hours. And then again, model guidance was very limited. We had facsimile charts at 12-hour intervals. The models went out to 24 to 36 hours. They would, from 0Z the evening before, may cover the convective day, and that's it. We had the LFM, limited area fine mesh. It wasn't particularly fine, but it was at the time. The grid spacing was 190.5 kilometers. We're typically looking at high resolution models today with 3-kilometer grid spacing and anywhere from 50 to 60 to 100 vertical layers. The LFM had 6 vertical layers. The primitive equation model had even less horizontal resolution, 381-kilometer grid spacing, and again, 6 layers. So what you had in terms of model guidance was relatively limited compared to anything that we have today. Here's an example of the work area in cells at this particular time. You can see the map wall behind the forecasters, and we have these sloping desks for chart analysis, which I found was really, really nice to have because you could spread out and there was a lot of room there. What we had were the NWP fax charts. You can see those in the middle there. Hand-analyzed upper air charts on the left, and a hand-analyzed CONUS surface chart, which was done every 6 hours on the right. That's where I cut my teeth on doing surface analysis and doing the US map that included southern Canada during my earlier years in cells. Here's an example of the type of fax maps that we had. This was the primitive equation model forecast from 0Z the evening before the April 3rd outbreak, and then showing the 12, 24, and 36-hour forecasts of the upper air system. We paid a lot of attention to what we call PVA, or differential cyclonic vorticity advection at that time, in order to highlight areas where there was potentially synoptic scale ascent, and follow this through this 36-hour period. Here's an example of a hand analysis of a computer plotted chart. This was from 0Z, again, on the 3rd of April. The data were plotted by computer. We had to draw the wind barbs by hand at the time, and the analysis was in some detail, certainly looking for regions of maximum wind. You can see here in Oklahoma, difluent flow in the mid-levels, which may enhance large-scale ascent in the area. Similar charts were analyzed at 700, 850, and the upper jet levels. And along with soundings, these were really the cornerstone for short-term analysis and forecasting at cells at that particular time. Now, recall I showed you this composite chart from Pawlish and Miller. We also did that at times. Here's an example of the composite chart from observational upper air data from 0Z on April 3rd. The different colors correspond to different levels in the atmosphere. But again, you can see where the jets are, where the moisture axis is, and the features coming together, which may help to develop severe weather in certain regions. If we can do it with observational data, we can also do it with model data. This was using 24-hour LFM model features to produce a forecast composite chart. And this, again, would allow the forecaster who is making the outlook to have a better sense of where key parameters were coming together that would influence the development of severe weather. So radar, this is what we had for radar. This is actually a color-enhanced version of the radar summary chart. It was hand-plotted and then analyzed every hour. This one, again, was color-enhanced. This is from 2135Z on April 3rd. And the thing that you notice right away are three convective lines showing up here. Steve Corfiti is going to talk more about this when he discusses the meteorology of the situation. By this time of day, there were at least three tornado-producing lines of severe storms. We could not look at the local radars directly, other than the Kansas City radar. We didn't see radar reflectivity mosaics. There was no animation. This is what we saw. And we focused on where the maximum tops were, because that's where we thought the cores of the storms would be, the most intense updrafts. And you can see some of these tops in Kentucky are up to 65,000 feet reported by the radar operators at this particular time. So there's information on coverage, maximum tops, max intensity, intensity trends, and movement. But this is what we had for radar at the time. It doesn't look particularly advanced, and it wasn't, but we were very fortunate at CELS to have all of this information coming into NSS-FC. So this is an example of the satellite. It was an ATS-3 visible satellite imagery at about that same time. And you can see these three lines or bands of storms in here. Again, these were available with about 30 to 40 minute latency after the image time. There was only visible imagery. ATS-3 at the time did not have infrared for nighttime. And it was these hard copy images that were used to make a satellite loop that we saw every 6 hours. This is an example of it. And one of the things you're going to see is it appears as if the navigation is unsteady. This has been shown, especially over some of the last few days of people talking about the April 3rd outbreak. So some of you have probably seen this before, but you could see the resolution isn't as good as what certainly we have today, and the timeliness was not as good. This is an example of an outlook during that time, and this was the 9Z 24-hour convective outlook that was issued on this day by Roy Guerra. He was the outlook forecaster, and the facts chart is broken up into two 12-hour periods, 12 to 0Z on the left, 0Z to 12Z on the right for the full convective day. It's hand-drawn, and then input into the facsimile system at NSS-FC. At the time it was issued, there were two watches in effect from across some of the Arklatex region in toward the Missouri Boot Hill, and these were also drawn on here. And it says scattered severe thunderstorms. So it might be confusing to some folks. At the time, we used coverage of severe thunderstorms, somewhat similar to the coverage of any type of convective weather or showery precipitation. Scattered was the third category level. I never saw numerous issued I never saw scattered issued except for this. These terms went away by 1980 when the risk categories came into effect. There was also a short discussion. This is the entire discussion. The first paragraph talks about scattered severe thunderstorms expected today and tonight, and it describes portions of states. And then the second sentence gives a brief meteorological explanation. Strong low pressure area expected in the northeast Missouri by 0Z, with cold front southward through eastern Arkansas. Strong southerly winds with cooling aloft expected to give severe thunderstorms. Activity spreading eastward during the period. That was it. That was the entire discussion at the time. We didn't go into a lot of detail in most situations, even a situation such as April 3rd. I want to show you now surface analysis. This was the 21Z hand-drawn surface chart that Clarence David, who was the lead forecaster on the evening shift, was working with at this particular time. This is the pressure and wind chart. We actually had what we call hourly check charts. One map would have pressure and wind, the next map would have temperature and dew point, and the third map would have clouds and weather. We couldn't combine it all because of the limitations of the line printer that was used at the time. But one of the things you can see on there is the hand-drawn parallelograms, the rectangles of watches that were either in effect or were about to be issued. I'm going to highlight in this red box up here, this watch. It's hard to tell from southern Lake Michigan down into eastern Illinois and Indiana. This is the microfilm of the watch. At the time, we used multi-carbon paper forms to type the watch information on there. And then the top form would be given to a communicator who would cut the teletype tape to transmit this on teletype circuits to disseminate it out of NSSFC. It's a little hard to read because the microfilm obviously was old at the time, but this is what it said. National Weather Service has issued a tornado watch, very similar to what we say today. Southern Lake Michigan, in portions of states, threat of tornadoes will exist in these areas from 5 p.m. until 11 p.m. and mentioned it with anchor points would be from Grand Rapids, Michigan to Evansville. And if you look in the lower left-hand corner of this chart, you can see it written down there, Grand Rapids, Michigan to Evansville. This was one of many, many watches issued on this particular day by cells. I'm going to go through very quickly watches issued during this time. This is during the daylight hours, but there were 30 watches issued during the event. This is watches 92 through 98 that went into 7 p.m. And one of the things you will notice is a lot of overlap in some of the watches, and this did generate confusion within some of the Weather Service offices, as well as in the media and the public. The next series of watches were issued from mid-afternoon into the nighttime hours. And as you can tell, there was a lot of watch housekeeping performed during this time to reduce the amount of overlap and reduce the amount of confusion. More watches issued from the evening hours well into the overnight hours, watches 105 to 108 through 4 a.m. And as we go into the next day, other watches that continued from 11 p.m. until 1 p.m. on April 4th. And then the last in the series, the final watches along the East Coast. Most of the severe weather occurred on April 3rd, and particularly between noon and midnight on April 3rd. So this is the large area that was affected by watches on this particular day, which were in effect for at least 33 consecutive. So I'm just going to summarize a little bit here. The disaster survey report made a number of findings and recommendations. I'll highlight a few. In terms of number of tornadoes, lengths of tracks, of area affected, etc., outbreak was the greatest in recorded history. What recommendations did they come up with? Well, the first one is similar to what we will still hear today. Improve public tornado education, safety training, community and school preparedness, improve spotter networks, establish warning sirens, etc. This doesn't change. We're done a lot, obviously, in 50 years, but there's always a need to do more. Part of the challenge on this day was the communication system, the teletype system was incapable of transmitting so many warnings for this episode. I think there were almost 150 tornado warnings that were issued. All of these warnings had to be hand prepared, cut on teletype, and many of the circuits became overloaded, and some warnings did not get transmitted, especially across state lines, until the warnings had expired. So one of the things, NOAA Weather Radio was just starting at that time. They wanted to expand NOAA Weather Radio to improve warning dissemination. There were very old radars at some of the local warning offices that even had radar. Many did not. There were two vintage military repurposed radars, what were called the WSR-3, WSR-4. And between 1976 and 1980, a number of new local warning radars were implemented, the WSR-74Cs. And then move ahead with the automation of field operations and services, or AFOS, improve data flow, message and forecast preparation, and product dissemination to bring things up to standards that you might be able to handle an outbreak of this type better in the future. There was one that affected cells in particular, was to establish a techniques development staff at NSSFC to merge new and conventional data into improved techniques for forecasts and warnings. This is a picture of the original TDU staff. Some of the folks obviously went on to very illustrious and renowned careers. You can see Les Lemon, Joe Schaefer, and Chuck Doswell, and Rich McNulty were the meteorologists. And these folks certainly became internationally renowned. One thing that came out of this that I want to mention is a transformative change was the installation of a specific for cells Mercatus-based system. Mercatus was the man-computer interactive data access system developed at the University of Wisconsin, and TDU and cells worked closely to collaborate with Wisconsin to first have an experimental system set up in 1980 that connected to the database at Wisconsin, and then in 1982 installed the Centralized Storm Information System, is what it was called, or CSIS. It was the first operational system in the Weather Service to have interactive displays of real-time data, satellite observations, derived fields. There's a picture of SPC forecaster Larry Wilson at the time. And this was transformative in that we could finally see in real time weather systems, weather data, and it changed the way we issued watches. Where watches had been purely forecast with lead time of 1, 2, even 3 hours. Watches issued at 1 p.m. Valid time doesn't start till 3. But once you're able to see the cumulus fields, towering Q, boundaries, you can place watches more accurately and in a more timely manner. This had a major impact on SPC. So I'm going to stop now. Appreciate your attention. And I am going to, I believe, stop screen sharing at this point. And I'm also going to stop talking because Steve Corfidi is now going to get into the good stuff. Mine was the appetizer. Now we're going to come to the main course.
So while Steve is switching over, I think one of the things that's been interesting is some of the comments that we've received while you've been talking, Steve, is that you're taking us back to undergraduate with hand-drawn analysis. You know, for me personally, I was looking at that going, wow, that takes me back to Paul Reuscher's synoptic lab, synoptic 1 lab in undergraduate. So we've gotten a lot of comments about that. So thank you so much for sharing all of that. That was great background information. And now we're actually getting to the meat of the actual event. So Steve, are you ready to share your screen?
Yes, Melissa, thanks. And
all right.
Can everybody see that?
Just need to put it into presentation mode and I think you're good. Yes, sir. You're good to go.
All right, thank you. And Steve, that was a great review of the state of the art in severe weather forecasting 50 years ago. And I just really appreciate that historical perspective you provided. And as you said, we'll look at some of the output, how it was utilized at that time. And I think worth mentioning too, just backing up just a bit at the beginning of this talk, the SPC, what became the SPC, the old CEL, Severe Local Storm Unit, and NSSFC are unique in the Weather Service. And I think you could argue probably around the world, and that group was centered on, and its heritage was based on mining observational data to do the forecasts. And Steve said, even as recently as 40 years ago, the models were still relatively crude compared to what we have available today. And so it required the mining of data, observational data, as fast as the forecasters could get their hand on it, to kind of come up with a picture, a snapshot of the atmosphere, what it was doing, and then based on their understanding of the conceptual model of how the atmosphere behaved, both on a larger scale and the smaller mesoscales, how that might translate into producing severe weather. So I think Steve's presentation really gave you a flavor for that. And still to this day, I think the SPC is unique in that we do focus, or it does focus, on observational data. Well, as Steve and Melissa have said, we're going to look at the just in a very high level look. We'd love to get down into the smaller storm scales, but obviously the data wasn't collected at that resolution back in the day, as Steve said. So we're going to have to limit our presentation here to try to find whatever smoking guns that might have existed at that time to create such a momentous event. As Melissa presented earlier, I mean, arguably this is still the most outstanding event for the last 150 years by various metrics. The number of F4 and F5s on the order of 30, up to 15 or 16 tornadoes in progress at one time. So it's just interesting to compare the super outbreak in 1974 here, just with the notable events of the last 150 years. Most of this data, thanks to Tom Grzoulis for his monumental book and assembling all that data. And if you kind of lay out those high-end outbreaks since the 1800s, you see the super outbreak in 1974 stands head and shoulders above the rest, in particular, again, in the number of intense tornadoes and just simply the total number of the area, square miles covered by the severe weather outbreak. Even in the more modern times, say going back to mid-20th century, you can see, and these outbreaks are arranged chronologically, you can see really until the 2011 southeastern event, the super outbreak still, by many metrics, is still very, very much in prominence. So we'll try to look at some of the reasons why that was the case. And certainly as a forecaster, I go back into the early 80s myself, and the super outbreak was always the gold standard. And as a forecaster, of course, especially a young forecaster, you didn't want to miss the big one. And you would think there would be at least just one item that would be stand out head and shoulders above the rest in terms of the forecast fields, parameters that we look at for forecasting severe weather outbreaks. But as we'll see as we get into this presentation here, it certainly wasn't just one aspect of that event that was outstanding, but actually multiple aspects of the environment. Just one other metric here, thanks to Harold Brooks for this slide. It only goes up to 2013, but I don't believe that the record count, this shows just graphically, as the display says, maximum annual 7-day F2 or greater tornado count. And you can see that early April period, which was really 1974, was really an 18-hour period beginning at roughly midday, 18 Zulu on the 3rd of April and ending the following morning around 12 Zulu. That 18-hour period had more F2 or greater tornadoes than any time before in recorded history or since. So just one more metric showing how outstanding that event was. And, you know, obviously there's been several other very significant outbreaks that are shown in this time span, but they just fall slightly below that in terms of coverage of high-end tornadoes. As Steve said, Miller Type B, or just a classic Southern Central Plains, Mississippi Valley springtime tornado outbreak, is certainly what the 1974 super outbreak was. but it was on a grander scale, much grander scale. And of course, the schematic that appears there in the lower right, that's from Newton's classic 1967 paper, and Steve illustrated the Fallbush and Miller schematic, looks much the same. And that's associated with basically the ingredients being brought together by strong Colorado or lee side of the Rocky Mountain cyclogenesis, where you get southerly low-level flow advecting the fuel, if you will, for deep moist convective development, moisture, and then overlain by westerly flow at the jet stream level, mid and upper levels of the troposphere, and in particular, cooling aloft and ascent downstream from a well-defined shortwave trough. And as Steve said, back in the day, we used to say positive vorticity advection or differential cyclonic vorticity advection, but basically what you're talking about is divergence in the upper levels of the atmosphere downstream from a trough. And as the air parcels move through the trough, conservation of vorticity, they start to expand, just like skaters expand their arms where they want to skate or rotate more slowly. And that expansion of air parcels aloft, that's that divergence, it's just tantamount to saying differential positive vorticity advection, causes ascent in a broad zone downstream from a trough. And the trough in this case shown by the depression or U-shape in these contours, height contours with the dashed lines. At the surface, the reflection, this is actual hand-drawn surface analysis like the one that Steve was talking about. In this particular one, you can see the station plots with temperature, dew point, pressure, so forth. This was at 0Z, UTC, I won't say UTC just in the name of brevity here, 0 Zulu on Thursday, the 4th of April. So this would have been the surface map that was issued literally 50 years ago at this moment for the CONUS and North American area by what was then the National Meteorological Center in Washington, D.C. area. And you can see two tornado reports actually hand-drawn on here, one here near Huntsville, Alabama, Northwest Alabama. I believe that was one in Limestone County, and one in the upstate part of South Carolina, both associated, well, this one in the east associated with band 1 that Steve noted on the satellite imagery, and this one here with the second band of severe weather. But just to give an idea of what the surface analyses look like on a national scale 50 years ago. This is just a broad overview using the daily weather map products, 500 millibars on the top panels, a surface on the bottom panels, showing the evolution of features during the 48-hour period from the morning of the previous day, Tuesday, April 2nd. And our calendar this year is, at least after leap year day in the end of February, is the same as 1974's. And so if I speak of Monday, Tuesday, and Wednesday, we're the same days of the week as are today. So this was Tuesday morning on the left, Wednesday morning in the middle, and Thursday morning on the right. And you can see the general pattern at upper levels of the atmosphere. Let's just say the jet level, we'll say 500 millibars, had a broad, largely zonal pattern over the United States and North America that changed rather abruptly to a more highly amplified pattern. And we'll see in subsequent slides here why I think that was so important into, if there was one smoking gun, so to speak, that probably the greatest weight would have to be put on that particular aspect of this event. We'll look at that more closely. And in response to that change from zonal to more highly amplified jet stream regime, you see the Colorado or lee cyclogenesis, which at one point actually encompassed, the surface low encompassed about 2/3 or better of the lower part of the United States, the continental United States. One of the nice things you can do in hindsight is go back and look at what happened back in the day, so to speak. And particularly, a lot of this data now is available almost in real time online. But back in the 1970s, you would have to wait for the publication, the AMS publication, well, still the Weather Service publication, I believe at that time, monthly weather review, which would produce these very nice monthly summaries of the upper air patterns that had occurred or were in place for that month. And this is from the June 19th, these panels here from the June 1974 edition of one of those articles that was looking at the pattern that was in place for March 1974. And I think, again, there's some key takeaways here as to why the 1974 outbreak was so outstanding. I know most folks probably watching this presentation don't look at these charts every day. The one on the top left here is a mean 700 millibar. Back in those days, they were looking more at the 700 millibar level, but this would be very close to what you would see if this were actually a 500 millibar height pattern. So just think of these as elevation contours of the 700 millibar pressure surface, and where it's warmer, the heights are higher, so they're higher in the equatorial region all the way around the edge of the display, and they're lower over the pole because the air is colder, and so the heights that you have to go up in the atmosphere to reach a 700 millibar level are lower. So the screaming message here, if you don't look at these every day, is this very broad cyclonic, weekly low amplitude cyclonic flow, or a jet stream, extending all the way from the East Pacific there off the coast of Korea and Japan, clear across the Pacific into the area just west of the continental United States. Very unusual to see such a broad expanse of fast jet stream flow, particularly to have a monthly signal that long. And really what that was telling us is that it was unusually cool across the North Pacific, the Aleutians and Kamchatka area and Alaska, all across for that whole entire month, and probably a little bit warmer than normal farther south in the trade winds regime and then near Hawaii. And that persisted for the entire month, that fast flow. If we look to the right side of the same display, and again, these panels are coming from that same article, this is a look at the last 6 days or so of the month of March 1974, and you can see that pattern still in place. A little bit relaxation of the flow over the Western Pacific, but a very strong jet implied by this enhanced gradient area of the 700 millibar contours across the Central and Eastern Pacific, and a well-defined, even averaged over a 5-day period, shortwave trough just approaching the coast there at the end of the month of March 1974. So what does this have? What effect does this have over sensible weather and downstream across the continental United States? Everybody here is familiar with, of course, the Enzo, La Nina, El Nino, La Nina pattern. And I'm sure Ashton will elaborate a little bit on this later in the presentation. But this was a La Nina pattern. The winter of 1973-74 was a La Nina pattern. As you might expect with that pattern, above normal temperatures prevailed across the continental United States for somewhat different reasons than we had just with this past winter. These are the temperature departures of normal for the entire month here on the lower left panel, and the last 5 or 6 days of the month of March 74 on the right. And you can see the signal very strong with temperatures running for the entire month in that area from the Great Basin, east-southeast into the southern plains, anywhere from 6 to 9 degrees above normal across the Four Corners region and the southern plains. And similarly, even more stronger departures from normal, up to 12 degrees across much of that same region in the latter part of March. So what does that do in terms of sensible weather? Well, obviously, that strong westerly flow, westerly momentum across a mountain chain, as we all know, those of you out there are meteorologists, conservation foretells potential vorticity. That favors development of lee cyclones, a downssloping flow off of the Rockies. You have compressionable warming. So basically that sets the stage for an unusually warm and potentially dry pattern in the southern plains. But particularly there's going to be a lot of warmth, especially along the jet axis as it's coming across along and south of the jet axis as it's coming across the Great Basin and into the southern Rockies. And that same pattern shows up here just more colorfully in these panels that are looking also at the 700 millibar flow. In fact, this panel, my panel that I just showed in color, this right here is exactly what you're seeing in black and white on the panel from the Monthly Weather Review article. And you can see that strong momentum, westerly flow across the East Pacific, and a trough here in the thickness field just about to enter the western part of the United States. And here are the anomalies. This is just showing the anomalies in both the height and the thickness through that period. And you can see for the full 30 or 31-day period in March 1974, how strong the departures from normal in the 1,000 to 500, and just again for the brevity, I won't say hectopascals, we'll say millibars, 1,000 to 500 millibar surface. Thickness, much like with the height contours, the greater the thickness, the greater the warmth or mean temperature in the column when the thickness is just talking about literally the vertical thickness between the surface, the 500 millibar surface up there in mid levels of the atmosphere, troposphere, and the 1,000 millibar surface, which is roughly near the surface in the ground. And 60-meter departures from normal averaged over the course of the entire month across the Red River Valley area. And you can see that warmth extending all the way from the Great Basin into the southeast. Another way of looking at things in terms of the hemisphere, and then we're going to focus down more on the synoptic scale and then eventually a little bit of the mesoscale. This is just showing how much energy was in those various scales during the period from March into April of 1974. Remember when we go back to here, we looked at this hemispheric pattern, and this is just basically one large scale trough. If you look at this maybe from the distance of the moon, if you could look back at the North Pole from the moon, you would see that essentially just one broad or planetary scale synoptic trough or low, if you will, extending all the way from the, Northwest Pacific into the North Atlantic. And just a few kinks here, maybe over Scandinavia, and maybe a little bit down here off the coast of Florida in terms of anticyclonic patterns. So most of the energy in the atmosphere is in these low wave numbers. It's just saying there's one giant wave essentially in the jet stream pattern. And that shows up with this very strong peak with these N, that's wave number one, meaning that most of the energy in the atmosphere through the latter part of March in particular was concentrated in that one large scale planetary wave. But once that deamplification occurred, which was associated with the arrival of that strong band of flow and the associated shortwave trough into the lee slopes of the Rockies, you see a downstream breakdown of that hemispheric one wave pattern into a lot more energy into these smaller wave numbers, which are basically just your synoptic scale troughs and ridges that we're more familiar with, similar to the one that just went through the central and eastern United States here in the last day or so. They would be wave numbers 2 and 3, your typical synoptic or large synoptic scale waves versus these very large planetary scale waves. So even on this hemispheric scale, the transition which occurred during the super outbreak in 1974 is well demonstrated in this analysis, wave analysis. And I thank Bob Rabin, now retired from the National Severe Storm Lab, for that panel there. And again, here's the one wave pattern essentially across the whole northern hemisphere. Well, now we'll try to bury down just a little bit into the synoptic scale. We're going to go kind of fast, I guess, through this. There's just so much we can only present here in a few minutes. These were hand analyses, and Steve Weiss and other legendary lead forecasters at the Severe Storm Center drilled into me the importance of doing hand analysis. And like everybody else, even by the time I came along, it's like, why would I want to do hand analyses? I can get an objective analysis in 2 seconds. Even then, I could see the map, a 500 millibar map from the analysis from the LFM model or the spectral or PE model of its day. But honestly, it didn't need to be drilled into me very long to see the errors of relying on the smoothing techniques were used, particularly back in that time, because of the large grid, or the not very well resolved large grid that were used that Steve talked about. So by being able to do analyses by hand, you're not obviously doing kind of a data fusion here. You're not just looking at the, and by the way, the 850 charts and all of what you're going to see the next several slides. 850 is in the upper right, the 700 millibar analysis in the upper left, 850, 700 in the upper right, 500 in the lower left, and 250 millibars, so basically the jet stream level, top of the troposphere in the lower right. By doing the data fusion, these analyses don't just represent the data that is displayed on any one of these panels, but it also displays, of course, inclusion of satellite data where available, other levels, so you're kind of integrating in the vertical in your head when you draw the analyses, and any other data you can get your hand on. And again, nowadays we have a lot more data at our disposal to even do a better job at hand analysis, but unfortunately there's so many other things vying for your time that we all know that hand analysis, hook or by crook, is starting to fade away. But there's a lot of value in doing these by hand, even though they look like, and I've had my kids and others say, why do you take color crayons to your job every day before I left the SPC? But there was a method to the madness. All through these analyses, I've highlighted Kansas and Missouri just for not only because cells used to be located in Kansas City, but also because it's just in the center of the map and it helps get your bearings as you go through these. Okay, so this starts on the morning of Tuesday, the 2nd of April, the morning before the event. And there was actually a severe outbreak of some proportions across much the same area that was affected by that of the super outbreak 2 days later across the Southeast in Tennessee Valley. And you can see the residual low-level jet stream, I'll just say low-level jet, just starting to exit the Carolinas the morning of the 2nd following that outbreak. And there were actually several F3 tornadoes and some fatalities in the Southeast that day. And the shortwave trough associated with that was just about to exit the coast. And you can see at 250 millibars, a well-defined jet streak exiting crossing the Appalachians at that time in response or associated with that event. Upstream, you can see the beginning of the strong band of flow starting to impinge on the Western United States. And of course, that's just what we were seeing earlier here with that strong band of flow and upper trough poised to come into the Western United States. So by the morning of Tuesday, the 2nd, the strong jet streak had come into northern central California. And more important to note, in the next 12 hours particularly, was the strong long stream variation in the wind speeds. So you have on the order of 150 knots here across the area near San Francisco Bay, decreasing to the order of 70 knot flow at 250 millibars over the Red River Valley region of Oklahoma and Texas. So there's a very strong, a long stream variation of the flow in that corridor, which is probably about 1,000 miles long. And again, another prime ingredient for favoring strong cyclogenesis in response to the ageostrophic forcing that gets going. And you'll see evidence of that in upcoming charts. So the strong jet stream, the forced ascent over the plateau and Rockies, and then the descent and conservation of potential vorticity, strongly favoring strongly cyclogenesis over eastern Colorado. And you can see that between the morning of the 2nd, Tuesday, the day before the event, and the evening of the 2nd, 0Z, on the 3rd, and the associated development of a low-level jet stream by evening from Texas up through the southern half of the plains with speeds of 50 knots in Oklahoma City area. Upstream from that region, the cooling, the onset of cooling associated with that approaching jet streak, just about getting into the southern high plains, Colorado and northern New Mexico. But out ahead of that, there's this weak feature that shows up, and it's subtle, but it comes out across the southern plains on the evening of the 3rd, Wednesday, Tuesday, the 3rd of the 2nd, 0Z, Tuesday night, 0Z, the 3rd of April. So this was the night before the event. And you can see those temperatures decreasing across the Texas Panhandle and even into Oklahoma with the arrival of a thermal gradient at 700 millibars. And it's highlighted there in that red area, running out ahead of the more obvious jet streak and up shortwave trough that's still hanging back over the approaching the Rockies and from the Great Basin. That feature continued east into the mid-Mississippi Valley overnight, and in conjunction with the development of this low-level jet stream across the southern plains, actually gave rise to thunderstorms around the time that these analyses were going or were being made, upper air soundings were being made. And if you recall from Steve's analysis, it was actually some thunderstorms showing up in that one radar display that he showed, and they were associated with this shortwave impulse, I guess is a better word, some sort of at least area of ascent, probably manifested as weak positive vorticity advection, certainly some height falls at 500 and 700 millibars. It was spreading out well ahead of the main obvious shortwave trough, which showed up even on those analyses from the Monthly Weather Review article. Notice also what happens in the southeast during the next 12-hour period. Now we've advanced until the morning of the event. This is the morning of Wednesday, April 3rd. And we have a strikingly different 250 millibar chart from what you saw just 24 hours previous. There's the residual and still very impressive jet streak over the Ohio and Tennessee Valley there with 130 knots over Nashville. The next morning, we have shortwave ridging that's developed across that region, and the development of 110 knot or better jet streak across the upper Great Lakes and Ontario. And again, anybody who looks at upper air charts, any amount, and certainly like in connection with winter storms, as Lou Cellini or Paul Cosin would like to attest, this is clearly a situation with very well marked coupled jet environment, very favorable for large scale ascent, not only upper level divergence associated with the exit region of the jet streak that by this time now was well, by the morning of the 3rd, well into the southwestern United States there across Arizona, Southern California, and getting into the Southern Plains, but also divergence in the right entrance region of this jet streak across the upper Great Lakes. So in combination with that feature that we mentioned there coming out of the Southern Rockies ahead of the main shortwave trough, you have the development of a coupled jet structure, which certainly played some role in enhancing the divergence, the synoptic scale forcing for ascent across a large part, certainly the northern and western parts of that warm sector, which we'll talk about here in just a second. And we'll back up here and just go back again to the evening before. You can see with the Lee cyclogenesis just starting to get going there, the 850 panel by the next morning again has tightened up. This is a very impressive 850 millibar. Almost looks like this is a surface chart with a very strong cyclone center there just west of Topeka, Kansas. And again, it's circulation covering, really more than 3/4 of the United States. And in response to that, this enhanced south to southwesterly flow across the eastern third of the United States. So this low-level jet stream, of course, was developing in association with the increased divergence that was evolving over the mid-Mississippi Valley toward the lower Great Lakes. We fast forward here just into the evening of the event. So now we're really at the maximum of the outbreak. Again, 50 years ago at this time, it's really sobering to think. I mean, it should really take a moment of reflection to think that the tragic suffering that was going on right now across much of the region that we're talking about in response to these synoptic scale features put in place by that large and very strong jet streak that had migrated out of the Pacific into the southwest and now south central United States by this evening. And in response to that enhanced southerly flow, moisture on here is depicted in degrees Celsius. I apologize for the mixed match of US and metric units, but that's the way the operational community works, at least still working. So 12 and 16 reflect 12 and 16 degrees Celsius moisture, which of course is very moist, particularly for the time of the year across the southeastern United States. And again, just advecting the moisture that was left across the central Gulf Coast region by that previous shortwave trough, which was responsible for the outbreak 2 days before. And again, a very well-defined coupled jet structure in place across the eastern part of the United States. By the next morning, the continued progression and amplification of the large-scale flow, again, go back and look at the pattern from 2 days before, was largely westerly flow at 250 millibars across the CONUS. And then by 12Z Thursday morning, as the event was winding down, a highly amplified pattern all the way up to 250 millibars. One thing to have a high amplification, perhaps up to the mid-levels of the atmosphere, but it's another thing to see such a high amplification occur on such a short time span across that broad a part of territory geography. But the flow was unidirectional at all levels, still very strong, greater than 100 knot flow at several stations here in the Ohio and Tennessee Valley that morning, but strongly unidirectional. Okay, I just thought for our non-meteorological folks maybe on board, I hate to use jargon and not explain it. So just real quick overview of severe weather forecasting terminology and some of the parameters, terms we're going to use here, fast and furious, in the next few minutes, just to again, kind of provide an idea of how all these larger scale, planetary scale, and synoptic scale ingredients were being brought together to form such an intense outbreak. Severe thunderstorms, like all thunderstorms, require 3 ingredients. They're necessary ingredients, like we say require, because if any one of them is missing, you're not going to get any thunderstorms. But severe thunderstorms require the addition of 1 more. Those ingredients, 1 through 4, are buoyancy, lift, and moisture. And it's pretty self-explanatory, I would think. Buoyancy is the tendency for updrafts to form in the atmosphere, just like updrafts would form on your stove if you put a pot of water and started to boil it. So how much is there a tendency for air parcels, chunks of air of various sizes, to rise on their own without any assistance from a mechanical source like a front, outflow boundary, and so forth? The second ingredient is lift, and that's what I just mentioned with the what we're talking about with getting a parcel to rise. The buoyant parcels rise without any external forcing. A lifting mechanism can help get parcels that may not ordinarily rise on their own volition to rise. One of the synoptic scale lifting mechanisms we've already talked about is differential positive vorticity advection or upper level divergence. Another one would be warm air advection, where air is forced to rise up sloped surfaces of constant energy, call them isentropic surfaces or frontal surfaces, if you will. That is a form of synoptic scale ascent. Lift can also take the form of mesoscale sources of ascent. Those are the ones we described, like I said, along fronts, outflow boundaries, dry lines, terrain, so forth. And it can have smaller scale sources of ascent, like those associated with the rear flank downdrafts, for instance, along supercell thunderstorms that can enhance low-level ascent. So there's a lot of different kinds of forms of ascent. They occur on various scales, and of all the other necessary ingredients for severe storm, lift is the hardest nut to crack, the hardest one to forecast, because it's the hardest one to conceptualize and understand and see how it behaves in 4 dimensions of space, 3 dimensions of space, and in time. But so we'll come back to that thought in just a little bit. Moisture, obviously, we've talked about the fuel. You can have a lot of strong forcing for ascent, but if there's not enough moisture, you get dry convection, which can be interesting in its own right, but you're not going to get moist convection, which are the ones that bring us, unfortunately, large hail, damaging winds, and tornadoes. And finally, shear. Shear is what distinguishes ordinary thunderstorms. The presence of shear in the environment is what distinguishes ordinary thunderstorms from sustained long-lived thunderstorms. And the shear does this by 2 primary mechanisms, one of which, and shear, by the way, of course, is a change of wind direction and or speed with height. So shear accomplishes this by 2 primary mechanisms, one of which is just the tilt of the updraft. So if you have this schematic thunderstorm updraft here depicted by these cumulonimbus looking clouds here, the updrafts in the red, the downdrafts in blue. It tilts the updraft so that the precipitation cascade, which gives rise to the thunderstorm downdrafts through evaporative cooling and precipitation drag, that downdraft doesn't undercut the updraft and kill the updraft. So you might look at supercells as self-sustaining, kind of like, I hate to use this analogy, but it's a true one, kind of like a cancer cell. There's no self-destruct mechanism, and it's due to the presence of shear in a supercell storm. So the updrafts are tilted, but more importantly, the role of shear, and it's not only unidirectional shear, as in this 2-dimensional cross section I have here on the left, but also 3-dimensional shear. Of course, the real wind profiles can exhibit change in direction and or wind speed with height. So in this schematic here in the lower right, we're looking at a thunderstorm. Actually, this was taken by Ted Fujita in the early 1960s over Kansas, and you're looking at a thunderstorm from an aerial view in the late afternoon. So you're looking roughly northeast here. The low-level winds depicted in green are coming in out of roughly the south. Mid-level winds, let's say, up at 10,000 feet, maybe 15,000 feet out of the west-southwest. And then the upper-level winds are coming out of the west or maybe northwest. So there's directional change with height. And it's that directional change with height that is responsible for, along with the shear, the wind speed, the magnitude change with height, for the development of these horizontal roller circulations that get turned into the vertical by the updraft of the supercell. This is part and parcel of how a supercell forms. It's changing this horizontal rotation set up by these rolling motions, horizontal rollers, if you will, set up by the presence of shear in the layer, and that's tilted into the vertical by an updraft. So supercells are simply thunderstorms that have a persistent rotating updraft, and that rotating updraft gives rise to other mechanisms by which that updraft can persist and it doesn't self-destruct. There's pressure falls, because when that rotation occurs in the mid-levels of the atmosphere, there's actually a pressure reduction in the core of that rotating column of air that actually draws air in from around, and is one of the mechanisms, amongst others, that keeps supercells going longer than your average non-rotating updraft. And so they're almost like tops, like a toy top that will continue to spinning long after the original thermodynamics, which may have supported the supercell to form, have expired, or the supercell, the rotating updraft, has moved into drier or more convectively hostile environments. But again, lift is the most important and most difficult of those four ingredients to kind of assess. We talk about soundings. We look at soundings, and at the bottom here, photographs. So you'll hear this terminology, and I'll show just a few just a second. We look at SKU-Ts in this country. There are other ways of looking at thermodynamic data. Tepograms come to mind. The reason we look at SKU-Ts is because the temperature lines on these are sloped from lower left to upper right. So these dashed lines you see here from lower left to upper right are the temperature lines on this profile or display of thermodynamic data from, in this case, a sounding. I believe this was actually in Springfield, Missouri, not too many years ago. But the point is, you're seeing the data displayed, the temperature profiles in red, and the observed moisture profile in green. And the reason we like to look at SKU-T charts, it means it's just that the temperature lines are skewed, they're not vertical. And we call these SKU-Ts because at a glance, the forecaster can assess the strength of pressure or temperature falls with height, which are the lapse rates. I failed to mention that here on this previous slide, but the temperature change with height is the predominant way of assessing how much buoyancy you have in the atmosphere, and that's known as the lapse rate, temperature change with height. And you can see this stretch of this particular sounding from this level here, just below, and these are the levels in pressure, below 700 millibars up to about 500 millibars, there's a very strong pressure drop-off with height. So all other factors being equal, that would be a level or a layer of the atmosphere where the atmosphere wants to overturn. It's very conducive to updrafts and downdrafts, and it's because that temperature drop-off in the layer is very steep. And again, that's why we like to use SKU-Ts, at least in this country, to identify at a glance where these steep lapse rate layers are. And I love.
Hey, Steve.
Yeah.
Hey, we're gonna have to wrap up real quick because we still have to get to Bob and Ashton.
Okay. I don't want you to not see the analyses, so let's go. So there's what I call an EML, an elevated mixed layer. This is a plot of CAPE and SYN, which is just the inhibition, a warm layer aloft, which wants to keep the updrafts from developing for the period from the night before the event to the night of the event. And you can see over time, the shaded area that's depicted here, that's area that represents inhibition or resistance to convective development. But in spite of that, remember, there were thunderstorms that actually were forming in response to that low-level jet and that disturbance coming out of the southern plains over Oklahoma and Arkansas. So this is surface-based buoyancy. It doesn't get the whole answer here. It's just one of the many types why we have to use multiple types of charts. The CAPE, the positive area, this shaded yellow area here, is how much energy is available for updraft development. So the bigger that yellow area is, the larger the CAPE values you're going to see on these analyses. So the night of the event, there was CAPE only down here in the southeastern United States and along the Gulf Coast in response to that moisture ribbon at the low levels left by the previous shortwave trough. By the next morning, CAPE had increased markedly all the way up into the Tennessee, even the lower Ohio Valley. And there's also, though, a lot of persistence of this SYN or negative area, which again corresponds to the blue here, which is a lid to upper vertical motion. The updrafts would be marked by this dashed white line here. And an updraft can't get through that negative area or inhibition area because that area is warmer than the updraft trying to go through it. So it becomes negatively buoyant. It's like smoke hitting a ceiling, falls back down, spreads out. By the afternoon, with the sun coming out and simultaneously that moisture continuing at low levels to spread rapidly northward into the Ohio Valley, you can see the CAPE has spread, surface-based CAPE now has spread well into the Midwest and in across the Tennessee Valley and even up into the lower Great Lakes. And the inhibition depicted by the blue is just about gone. And by evening that same day, higher CAPE even is focused down here across the southern Appalachians and into northern Mississippi and northern Alabama. This is also exhibited here. This is the what I'm showing here is the EML, or elevated mixed layer, which is basically this steep lapse rate environment here that we talked about in our sample sounding. And what we're talking about is the arrival of a warm plume of air that originated out over the southwestern deserts and southern Rockies days before, in response to that persistent warm anomaly across the region, being carried across the southeastern or south central plains, south central United States, into the southeastern United States, and even sinking motion on the southern side of that jet stream coming out of the southern Rockies. So the darker the red and orange shades here, the stronger and the deeper that lapse rate environment is, overlying the moisture over the east central part of the United States. And this is just a huge area to see an EML in such a broad region in the United States and persist for basically up to 24 hours at a time, from the evening of the 3rd through the evening of the 4th. The only thing you can see that it starts to get eroded or consumed, if you will, by convective overturning in the across the region by the strong thunderstorms that are occurring in the region. But these are very steep lapse rates. These are the temperature drop in that layer, and that's saying the temperature drops are in the order of 8 to almost 9 degrees per kilometer across the mid-Mississippi Valley region. So that's a lot of potential energy for updrafts if you can get a mesoscale forcing for ascent, a front, a dry line, something underneath of that cap to break through the inhibition presented by that layer. And you can see that happening.
Thank you very much. And I mean, this is just kind of going into the complexity when it comes to these particular events. These large scale events, you know, it's the meteorology behind them is really hard. But what is interesting is the research that comes out of these particular events and the outcomes. And that's where I'd like to bring Bob in and have him talk about some of those outcomes from this particular event.
Okay, well, thank you, Melissa. And gosh, it's such an honor and a treat to be on the panel with the two Steves and Ashton. I thank Amos for allowing me to be with you all. And I'm going to go off on a little tangent, but an extremely important one before Ashton brings us back to outbreaks. And this is some research that emerged directly from the 1974 outbreak and has just been a tremendous revolution in meteorology and public safety. So I'm going to get us into slide mode. Is this working? Okay, good. Sorry. So I don't know how many of you recognize this person. This is Ted Fujita, of course, famous for the Fujita scale. But he has had many, many research tendrils. He was a brilliant, brilliant artist, as you can see in some of the sketches that we saw that the Steves presented. His work goes back to the 1950s. By 1970, had already developed the original Fujita scale. But this event took him in a whole different direction, which we'll get to. He flew over the outbreak a few days afterward and did a massive survey. And just to show kind of what not only a brilliant guy, but kind of quirky at times, he wanted to name it initially the Jumbo outbreak because of happening in 1974, so 74, and it was the fourth month of the year, April, so 747, which was the numerical acronym for jumbo jets. So anyway, if you ever hear Jumbo outbreak, that's where this comes from. So a major field survey, 3,600 color images of 93 tornado paths, and among other things demonstrated that tornadoes can go over mountains, down into canyons. So there was a bit of a folk legend back then, the tornado or the mountain will protect us, or the river valley will protect us, and his work helped show that's not the case. He demonstrated cyclonic or cycloidal damage paths. You can see the curlicues as multiple vortices, which I'm sure you've all seen on videos, rotate around the tornado as the tornado itself moves. So that's an important concept that he demonstrated amply in this work. But he also discovered another damage pattern. And interestingly, in his initial report, he didn't even talk about this other thing. I think he was kind of saving it to delve in more deeply. But in a book he published about 10 years later called The Downburst, he showed images like this. This is not a cycloidal damage path, but a starburst. So you can see something descended here and caused air to flow outward, kind of the opposite of a tornado bringing things in. And all these trees were felled. And this wasn't just an isolated incident. he said, hundreds of trees could be blown down in this, what he called a starburst pattern. And about 15% of the whole damage tracks he analyzed were these, what he initially called outbursts, later downbursts and microbursts. So 15% doesn't sound like a lot, but you had almost, over 2,500 damage path miles. So that's something like 400 miles of downburst patterns. So this took on added resonance just a year later when Eastern Airlines Flight 66 came down just before landing at JFK, deadliest U.S. air crash to date. And at this time, only a little over half of all U.S. people had even flown, right? Flying was still a little bit of a luxury, and events like this were pretty shocking. And you could see the debris in the foreground and the runway in the background. So Fujita surveyed this. The NSTB concluded this was probably interaction with a strong thunderstorm, but this is where Fujita first came up with the idea of downbursts that could basically escape notice from the anemometers that were then in place at airports. They just weren't doing the job. Well, he had to convince people, and as he later wrote, most meteorologists at the time believed that a downdraft, no matter how strong it might be, should weaken as it hits the surface, right? There was no doubt that downdrafts existed, but it just wasn't believed that that could be enough to bring a plane down. So he got to work and teamed up with the National Center for Atmospheric Research, which was at that time just developing its collaborations with other universities around the country, which is part of the reason it was created. So they teamed up with Fujita's home, University of Chicago, and got support from NOAA, NASA, and the FAA, and started some really revolutionary field projects. First one called Nimrod in Chicago, close enough to O'Hare so that it sampled the area near O'Hare. 3 Doppler radars, which at that time were not operational. Doppler was not yet in the Weather Service system. So these were experimental research radars, and 27 portable weather stations from NCAR, which were kind of a novelty at the time. So over 42 days, they captured quite a few microbursts. Follow-up study was at Denver's old Stapleton Airport, very close into town, and now a housing redevelopment. Again, 3 Doppler radars, 27 mesonet stations, lots of downbursts photographed in this project, in part because of infrared photographers present. There's an old United plane, the old United color scheme with the mesonet, a PAM station as they called them. You can see the downburst here. I think that's maybe a land spout over there. And here's the sequence of events. You see the air coming down and circulating in a curlicue. And near the end, we'll see a schematic of this. And one important difference between the Chicago study and the Denver study is dry microbursts versus wet ones. Chicago's were mostly wet, and Denver's were mostly dry, as keeping with the high plains, drier atmosphere, and both dangerous, but in different ways. Well, as bad luck would have it, right in the middle of this JAWS study in 1982, there was another catastrophe. Pan Am plane went down just less than 30 seconds after taking off in New Orleans in the middle of heavy rain, killed 153 people, just horrible tragedy, again attributed to a microburst right away, but there was no warning system. And this added impetus to get this work done. Fujita said the researchers felt this really needs to be understood quickly. So the next step was another project at Denver, but this was more operations oriented. It was really to develop the system that would go into airports within the next decade. On the left is John McCarthy, who led this study called CLAWS. You can see on the right a microburst and that pattern we were talking about and the airplanes in the foreground. This was taken by Wendy Abshire, a longtime friend of mine who was AMS education director until recently. She was part of this initial work. Here's the graphic I mentioned, how planes would go down. They would approach and veer up or tilt upward to try to compensate for the downdraft, but then they would get to the other side and the tailwind would slow them down and they would crash. So this research, not only on warning systems and how to deploy them, but pilot training as well, made a gigantic difference. And the data speak for themselves. There were more than 400 people killed in these accidents over just 13 years. But since 1995, there's not been a single person killed because of this, because of these systems deployed mainly in the early mid-1990s. John McCarthy, who I showed the picture of, in a recent BAMS article, called this one of the most successful and societally impactful research operations programs in the history of atmospheric science. And I have to agree, it's really, really something. And this might not have happened as quickly had it not been for the 1974 outbreak. So here's some more info, and I believe these links will be shared. And for those interested, this was a fantastic documentary. I bet some of you have seen it. It was aired on American Experience. You can find it, I believe, on Amazon Prime. And you can see this and some other teasers if you just go to PBS and look for Mr. Tornado. So with that, I'll hand it back to Melissa. Thank you.
Thank you, Bob. I think one of the most important parts of, when you get past these events is to go back and see what you could do better, what you can learn from, and how you can further the research. And this particular event really has furthered research in the operational side of it, the development of like what you just talked about, finding out about downdrafts, putting in this equipment to help save lives. And, Ashton, I know that you're going to carry on and you're going to talk more about that and kind of bring everything full circle. And so I'm going to pass this off to you to close us out on this really special webinar on this particular event.
Thanks, Melissa. And I know we're kind of long on time, so I'll try to be brief and just talk about a few aspects of my understanding of historical tornado outbreaks. I decided to approach it by comparing April 74 to April 2011, but also integrate some of the information that I had done or things that I had looked at over the past several years leading up to my investigation of the tornado outbreak, of the 74 outbreak for my dissertation. Looking for the share screen. Here we go. Alrighty, so for those who don't know my story, my interest in tornadoes in general started very young. I was actually hit by a tornado, or what we believe was a tornado, in 1985. But fast forwarding, when I was a teenager, I lived at the very tip of this dot, and this is a prolific outbreak that hit Arkansas, one of the worst outbreaks in the state's history. And there was an F4 that carved a path right through Saline into Pulaski County and into the south side of Little Rock. So I was always afraid of storms, but I tracked that one. It was actually a long track supercell, like what Steve mentioned a little earlier, that tracked all the way from Hope, Arkansas, where President Clinton was born, right into Little Rock, and actually did more damage downstream. So that was kind of like a fear of storms that turned into a passion. And then when I went to Jackson State, I kind of learned a little bit about Mississippi's tornado history, and there was one event that kind of stuck out to me. That was the February 71 Mississippi Delta tornado outbreak. 121 people died, over 1,400 injuries were reported. And there were just a handful of supercells right in this local area that organized, developed mesocyclones, and then produced one F5 and two F4s across the western northern portions of the state. One of the things I want to point out here is that there's actually radar data. So when I worked in Oklahoma, I had access to an archive with microfiche, and I kind of got geeked out and all excited and decided to start looking into this data set and looking to see what I can find to see how things were done back then, back in the 70s. What would the warnings look like? What the watches look like? And I came across this WSR 57 image. which is wild. They can actually make out hook echoes using the old technology back then. Now, I wouldn't want to be a warning forecaster necessarily with this moving through and having to warn based on hook echoes with just black and white images. Nowadays, we have things that are, our technology is a whole lot more advanced. We'll talk about that a little later. But some of the key takeaways from just that subset of research that I did was that the warnings in the 70s were the size of small tornado watches nowadays. I have a box here drawn that encompasses about 5 to 6 counties in the path of one of these supercells, and that's what a warning looked like. Way different than what it is nowadays. I also want to paint a picture. So imagine, and this is probably gruesome, unfortunately, but I was fascinated by it. Imagine these large, violent, half-mile wide tornadoes moving quickly through flat land in Mississippi, where sharecropping is still a thing in the early 70s. and entire families are living in these small shanty homes, surrounded by maybe or on a plantation. And those homes are just no match. They're worse than mobile homes for people to take shelter in. And so they're getting completely wiped out by these fast moving, F4 to F5 tornadoes, and entire families are being lost. And that was part of the reason why the death toll was so high with that storm, or with those storms that moved through western Mississippi. Another thing I learned about is that the warnings were verified based on the presence of hook geckos in addition to tornado reports. And I thought that was kind of fascinating too, because perhaps in the future we may get back to verifying warnings based on what we saw on radar. And in some regards, that's probably actually happening a lot now with storm surveys. Back then, again, the radars had no velocity data, and there were quote unquote good warnings. By today's standards, no, but back then those were good warnings, but there were still a high rate of casualties with these storms, partially because the communications were less clear and less effective than they are today. Some people didn't have TVs, radio, could you get the latest information? There's no Facebook, no Twitter, no cell phone. People were slow to get information. And by the time they recognized the danger was afoot, it was probably a little bit too late to respond. And then the last takeaway, if you look back through tornado climatology and you look at Mississippi and Alabama, they may not get the same frequency of tornadoes that the Great Plains does, but occasionally they get big tornadoes that move through. And sometimes those tornadoes can happen anywhere from November, December, January, February, March, and overnight. So those were some really interesting takeaways that I thought from the Mississippi outbreak in '71 that kind of fed into the '74 outbreak. So moving forward, imagine being a warning forecaster and having to warn based on these small hooks and these black and white images. That's a tough job, but that's what they had in place at the time in the '70s. And again, I learned about this just from my own independent research of the '71 outbreak and what I had available to me at the time. Here's radar-indicated supercells from the Covington, Kentucky, WSR 57. And here's an example of a tornado warning that I pulled from the WFO website for the Wilmington, Ohio forecast office. Again, it's already been talked about. There's been multiple rounds of fast-moving supercells that produced many tornadoes, or probably really effective and efficient tornado producers based on what we know about the event. And the warnings were based on radars and reports near the field, but they were large warnings spanning multiple counties. And again, no radio velocities, and there were also similar communication challenges. Steve already talked about this slide, so I won't belabor the point, but the '74 outbreak, and now starting to compare to the 2011 outbreak, where the term generational outbreaks were being used, where both outbreaks, based on a number of metrics, were among the most intense and deadliest in recorded history. We know again about the synoptic pattern for April 3rd, '74, large cyclone over the central U.S., and was not evident or obvious necessarily from this image, but a large area of strong instability and shear to support long-lasting supercells. We had the same type of environment actually in April 2011, but with a few key differences. So I'll just kind of move this first, and you can see that there's a departing low-level center, or a parting mid and upper level center there in the Western Great Lakes. Other thunderstorms forming over Arkansas, which is the finest state in the union, in my opinion. But then moving forward, these complexes kind of moved off to the east. And let me just stop here. These complexes kind of moved from west to east across the southern tier of the United States. But another system kind of dove down out of Arkansas and instigated these supercells that you see that formed. And this was the meat of the outbreak in 2011. Again, there was a really strongly sheared, strongly unstable environment, extreme parameter space supporting supercell thunderstorms with long track violent tornadoes. But the thing about this event is that parameter space was more confined to these southern states. There were a few tornadoes around the periphery of this area, but this was the meat of the outbreak. So a little bit different scale. Again, comparing the hook echoes that I just showed you to the radar reflectivity and velocity images that we see more commonly today, there's a whole lot more detail. And, a lot of research and analyses of these types of, reflectivity patterns here on the left and velocity patterns on the right have actually enabled the term analogy of tornado emergencies. And several of those were issued in this 2011 tornado outbreak. Also notice here that there's a hook echo, but there's a whole lot more detail, and there's a lot of higher reflectivities in this hook that's indicative actually not just of rain, but parts of homes, parts of vehicles, big chunks of debris that are being lofted into this supercell that was actually producing a near F4 to F5 type tornado at the time of this image. And again, here's a radar image. Most of you probably know this already, but there's strong inbounds right next to strong outbounds. This is indicating strong rotation. Again, they didn't have this technology in the 80s. They can only depend on just a fraction of what the information that this image on the left would show, which is basically just a hook echo. There's also been improvement in warnings, compared to 1971 and 74. Now we turn on the TV when we hear thunder and there's a broadcaster there telling us what's going to happen in the next few hours. And if there's something going on in our area, there was maybe a series of warnings. He's reading the warnings out because he's getting them either in print or on his tablet right there on air. And he's relaying that information. It's a whole lot different from what it used to be, where, information was a whole lot more sparse. Tornado reports took hours to come in sometimes, especially in rural areas. There might have been a lot of damage, but not a lot of reports slow to come in. I also notice here too on the right, the warnings that we used to have in the 70s were big blocks of counties, maybe several counties in an area that were being warned. Fast forward, this is a tornado, an active or a tornado emergency from 2011 for the Tuscaloosa to Birmingham tornado. And this polygon is more refined to the actual path of the supercell. So it's only covering parts of counties instead of the entire county or areas nearby. So we've got better warnings. Sometimes we have tower cams, live video showing large damaging tornadoes moving through an area in real time, faster communications. We have Twitter, Facebook. I can go out and take a picture right now and tag a forecast office, and they know immediately in near real time what's happening in the real atmosphere. Here's another example of an improvement, but this is more of a tricky one. Okay, so again, it's already been talked about that back in the 70s, real-time model data was a little bit challenging to get, and the models weren't nearly as advanced as what they are now, like what you see on the right. On the right-hand side, this is a very fine resolution model that can actually model individual thunderstorms and supercells with rotation. So this represents a pretty big breakthrough in the late 2000s and the early 2010s that Steve Weiss was actually a part of with the hazardous weather test bed that he was running for many years. But notice here, even though we've got this detail, we can kind of look and see that these storms are cellular. By other data sets and information, we know that they're probably in a really good environment. There's probably going to be a lot of tornadoes based on this. But the tricky part with these fine scale forecasts is that they're still wrong. Sometimes they're still wrong. In fact, most of them are still wrong. But what meteorologists have to do is understand the atmosphere, understand the general processes, understand what goes in the supercell development, what goes in the thunderstorm development, and how can you discriminate the two, and then come up with the conceptual model of how the atmosphere will behave, and then build a forecast around that. And so what I learned, and I'm really fortunate to have worked under Steve Kerfetti and Steve Weiss with, and learn these concepts, is that you still have to have a firm grasp of what the meteorology is telling you. You can't over rely on these very detailed images, these very detailed depictions of what's going to happen, because again, it's wrong. We know it's wrong. The weather models are not perfect. Having a background understanding of the weather can be really important. And sometimes in certain situations, forecasters may actually revert to the image that you see on the left just to get a general idea, as opposed to the specific outcomes that the higher resolution models can actually give us. So I talked a little bit about the differences between the 74 to 77, or the 71 to 74 outbreak and the 2011 outbreak. now I'll tie a little bit of that information, in particular with the tornado climatology, into what I did for El Nino, La Nina for my dissertation. So there's a graphic here on the left. I know we're short on time, so I'll spare you some of the details here, and we can talk about it offline if anyone has questions. But essentially, the 74 outbreak, which is actually reflected here in La Nina, fits really nicely within this envelope. You kind of expect that because, again, this tornado outbreak was actually one of the data points that was included in this series of gridded DPI, Destruction Potential Index here. But 2011 was not. So my past data set stopped at 2010. And notice here that there's a graphic that shows that most of the tornadoes in the meat of the outbreak occurred from Mississippi to Georgia and over to Tennessee. And of course, Alabama was the hardest hit. But now, how does that fit in the El Nino, La Nina theory, the scheme of things? Well, it kind of looks like it fits there in the southern part of the U.S. there in La Nina. Of course, 2011 was a La Nina, just like 1974 was. But I also want to point out, too, that there's also significant tornado activity that occurs in El Nino in April. So just because you have an El Nino or a La Nina in a particular area doesn't guarantee that you're going to have big tornadoes, or you might not even have tornadoes at all in some cases. There's individual factors that go into, what might be influencing where tornadoes occur on timescales like these. So with that said, I'll conclude. Again, we talked a little bit about this offline, but despite all of the improvements that we've seen over the past couple of generations of weather forecasting, the warnings, the communication, the dynamical models, the finer grid scale information that we're getting now, and even AI is starting to become a part of this, the death toll from the tornadoes in 2011 still rivaled the worst outbreaks in documented history. And there were some people, there were conflicting opinions about whether this could repeat itself before it happened. And one of the things I brought up to all of us in the panel in the side conversation we were having before we got on was that, there were some near misses in the late 2000s and the early 2010s that we were really fortunate that there weren't some bigger death tolls because tornadoes missed more populated areas and struck rural areas and did all sorts of damage. And that didn't happen in 2011. Joplin is another example. That one tornado killed over 150 people in one town. So there's a lot to learn here. I think if we don't improve our forecast and improve response and resiliency to tornadoes like this, I think we're going to get another outbreak like this again. So this is an important opportunity for the meteorological emergency management communities to understand how we used to do things, how things are changing, and how we need to keep changing to keep people safe and protect life and property. So with that, there's my email if you have any questions about any of this, or you want to talk about the El Nino-La Nina relationship or any other aspects of the work that I've done with tornado climatologies. And with that, I'll stop. And I just want to thank you again. And it's an honor to be on this panel. It's kind of cool to have a mini SBC reunion with Steve Weiss and Steve Graffiti on here. You guys have taught me so much over the years, and it's been a real pleasure and a blast to work with you all. So
thank you so much, Ashton. Thank you guys so much. I'd like to ask all our panelists to just go ahead and come back on screen as we get ready to close this out. And I think, Ashton, you kind of hit on this, and, we followed the event from, the beginning, what took place in 74, the process, what was going through the minds of those who were involved in the operations, to the research side of it, to where we are now. And I love how you brought in the emergency management community and clearer communications, because that interdisciplinary, mesh is really what is going to help improve, like you said, the communications and just the wealth of knowledge that you all have and were willing to share with us tonight. I know that we knew this was going to be a longer webinar than our normal, just because of the expertise on this panel and just this event. And so I personally would like to thank all of you, the panelists, for being with us and sharing your wealth of knowledge, and also for the 100 people that are still with us. This was one of probably our biggest webinar attendance in I know we did one on the eclipse yesterday, but just thinking about that, you guys it was like almost like a fire hose sometimes of information, but it was just so fascinating to see the process of how one event can trigger so many things. And, you know, even 50 years later, we're still learning from it. So again, thank you guys so much for being with us tonight and taking your time. So Eric, I'm going to go ahead and toss it to you to close us out.
Absolutely. I just want to say just thanks again to our fantastic panel and to you, Melissa, for putting everything together, being our moderator. Folks, for those of you, if you still have questions, I really would encourage you to go on to our online community and ask your questions there. You know, we have a really active community at amsweatherband.org. We can continue the conversation from this fantastic panel. So thank you all very much for joining us this evening. I hope you have a great night.